Today we're going to solve a combinatoric problem that I actually found from one of my old textbook. The original problem is actually given that the sequence a sub n is equal to negative of a sub n minus 2. And of course, I've already rewritten it into an explicit form, which is actually like the first part of the problem that want to find out the general solution. Then after that, there are also other parts, and the last part of the problem is trying to find out a unique solution given the conditions up here, which says a sub 0 is equal to 0 and a sub 1 is equal to 1. And of course, if we're just trying to use the given implicit expression for the sequence, we actually can quickly check that by listing out a few terms. We will have a sub 0 is of course 0, and then we have 1. And then after that, if we substitute in, we get a sub 2 is actually equal to 0 because we have negative of 0, which is 0. And then we have negative 1, and then back to 0, and back to 1, 0, negative 1, so on and so forth. And if you're very familiar of the trigonometric functions, you actually can realize that, of course, this is not the first term, the 0th term here. And the first term is actually equal to 1. Well, in fact, this is just the same as sine of 90 degrees, or pi over 2 if you're sticking with radians. And if you try to substitute in, you will see that it will actually work in general, that the expression will come out into sine of pi over 2 times n. And of course, you can just check it by replacing the n into whatever value you are, and then try to check if it matches the number in the sequence. So that's not much interesting if we're just trying to do it this way. So because of that, we're going to try to use the explicit function that we found in part A of the problem. Well, I kind of skipped a step here, but explicitly, we have the expression that actually involves with the imaginary unit I, and trying to see if we actually will end up with the same result here using the explicit function. And again, you can try to pause the video and try to work it yourself and see if it actually comes out to the same results that we actually found using the implicit function here for the sequence. And if you're ready to move on, let's do it. So how do we actually use this idea to get the unique solution? Well, all we need to do is substitute the initial conditions that we have here into our explicit solution, or general solution. So what do we get? So for the first condition, it says a sub 0 equals 0, which means when n is equal to 0, we have a sub 0, which is a sub n, is equal to, now we're going to substitute into our general solution, which gives us lambda 1, which is a parameter that we need to find out right now, times I to the 0th power plus lambda 2 times negative I to the 0th power. And of course, I to the 0th power and negative I to the 0th power are both equal to 1, so we can just rewrite it as lambda 1 plus lambda 2. Similarly, if we substitute n equals 1, we actually get a sub 1, which is actually equal to 1 here. And again, a sub 0 is just equal to 0 because of the initial condition. So we have a sub 1 here, which is equal to 1. It's equal to, now substitute to the right hand side of the general equation, we get lambda 1 times I to the 1st power plus lambda 2 times negative I to the 1st power. And if we try to simplify it, we will get lambda 1 times I minus lambda 2 times I. So now we actually get two equations here, and we have two variables. And again, those are parameters, lambda 1 and lambda 2. Then we can just try to solve it simultaneously by multiplying the first equation by I on both sides. And then we can just add the two equations together to find out that lambda 1 is equal to 1/2 over, 1/2 over I, or 1 over 2I. Similarly, if we try to subtract these two equations, we'll be able to find out what lambda 2 is, which is in fact negative 1 over 2I. And it should make sense because, again, one of them is adding, one of them is subtracting. So we should be able, we should actually get two different results. And if we substitute back, we should be able to see that lambda 1 and lambda 2 should cancel each other on the first one. And then when we substitute to the second equation, we'll be able to add them together to get one back. Good. So now we will be able to continue. So get back to the general equation. We can now say that a sub n is actually equal to 1 over 2I times I to the nth power plus, actually we have plus 1 over 2I but with a minus sign, so we actually need to rewrite as minus 1 over 2I times negative I all raised to the n power. And of course, you can try to simplify the n by putting it there and say it as I to the n minus 1 power, and then here we will change it to plus 1/2 negative I to the n minus 1 power. And again, because we can just put a negative down here, and we'll be able to rewrite the exponents into negative first power. But anyway, now we actually have the results, but it doesn't look like the unique solution that we actually found at the beginning, which says is actually equal to sine of pi over 2 times n. So what's going on? Let's verify it. See if we actually can get this result. Right, let's jump to the next board. Okay, so from the last board, we end up with the result a sub n is actually equal to the following expression explicitly for the given conditions up here. Then now we need to verify that if it is actually correct or not, because we said that from the beginning of the video, we should be able to end up into just simply sine of pi over 2 times n, which means that we'll be able to get all the values of a sub n into integers. And in fact, it will be a line between 0, 1, and negative 1 only. But in this expression here, we actually have the imaginary unit I here, so it's not easy to tell. Therefore, let's see if we can actually turn this expression into sine of pi over 2 times n. But to do that, we actually need to use the Euler identity, which says that I is actually in fact equal to e to the I times pi over 2 power. And for negative I, we'll actually get e to the negative I pi over 2 power. So as we do that, now we'll be able to substitute in, and we'll leave the fraction as it is. But for I, we'll replace it by e to the I pi over 2. And then we'll raise all of that to the nth power. So by the exponents rule, we'll just multiply them together to get e to the I pi over 2 n minus the second term, which is Similarly, we get e to the negative I pi over 2 times n in the exponent. Then we'll be able to put them together because they have the same denominator. And on top, we actually get e to the I pi over 2 to the n minus e to the negative I pi over 2 times n. Now up to here, what do we do? Well, we need to do the last thing, which is using the identity of sine of some angle theta is actually in fact equal to e to the I theta minus e to the negative I theta all over 2i. So let's see. We have the 2i on the bottom, which is great. Now on top, we have e to the I raised to times some power here, or some number here. Let's call that theta to be pi over 2 times n. Then for a second term, we also have that theta here. So we can in fact use this identity to substitute in to actually get the result sine of theta, which is the angle, and in this case it will be pi over 2 times n. And this actually matches to the initial results that we actually found at the beginning of the video. That's it. I hope you all enjoyed this video, and please don't forget to like and also subscribe to my channel so that you won't miss, you can find more of my other videos. And don't forget to turn on the notifications so that you won't miss any of my new videos either. If you have any thoughts, you can leave your comments down below. I'll see you guys in the next video.